Alright, so we're going to continue on with our Cartesian equation of the hyperbola. The last lesson we looked at when the hyperbola, the axis of symmetry is at the origin. And now we need to look at what happens when it's not at the origin. So we have a centre at HK over there. Right, so it's very similar to when it was off centre for the ellipse. Okay, so the equation's very similar except for the sign in between. That's the difference between your ellipse and your hyperbola. Okay, so the ellipse has a plus between them. Okay, and the value for A and B depends on the orientation where the foci lie. And for the hyperbola, there's a minus sign. Okay, so it's not dependent on A and B, it is actually dependent on whether the x squared bit is positive or whether the y squared bit is positive. Okay, and that will depend on your layout for your hyperbola. Right, so there's your equation, very similar to what the circle, but we're dividing by a squared and b squared, and both on the left hand side. You have it equal to 1 on the right hand side. So when this part, so this side is positive, okay, so I'm saying the negative sign with the y squared, okay, we've got our foci lying on the horizontal plane. Okay, so it's very similar to the setup of what the ellipse without the center, with the centre not the origin. Okay, in terms of your constant. So here's our centre, so everything works off that. Okay, so really just shifting the centre and then therefore shifting all these other dimensions around. Okay, so your sort of point where it intersects that rectangle, so we can draw the rectangle to be able to draw the asymptotes in, as well as the vertex for your hyperbola in the previous video. And that would be a useful way. So remember, the focus lies this side of your hyperbola and the directrices are inside, sort of between the two hyperbolas. Okay, so all those sort of conditions are similar, matching what we've done previously. Okay, so the eccentricity equation is still the same. Right, so the centre at HK changes your coordinate change of the foci, changes the equation to the directric, and also changes the equation to the asymptotes. Okay, so everything has a bit of a shift. That's all in your notes in there. So when y squared is greater than 0, so what I'm saying is the negatives with the x squared. Okay, so we've got what's called the conjugate hyperbola. Okay, so instead of opening out to the sides, okay, so we've got the foci lying in a vertical alignment, and we've got the hyperbola going upwards and downwards. So again, we can draw the rectangle with the dimension from the centre, which I haven't labelled. Alright, so the centre h, k. Okay, so if we know the values for A and B, right, so all we need to do is go upwards A, go downwards A, go upwards B, go downwards B, and then to the left A, and then to the right B. A. So A's are across, B's are ups and down. Okay, if we draw that rectangle with that dimension from the centre, okay, we can draw the asymptotes through the corners, right, and it'll also give us the intercepts of where the hyperbola touches that rectangle. Okay, so again, the directrices are inside your hyperbola, and the focus is on the. So when I say inside, I mean more like between the space where the hyperbola is not defined, and the actual foci are where within the region where the hyperbola is defined. Right, so this one we have, we're going to have a squared equals b squared outside of e squared minus 1 to the subject. Okay, so when we got this orientation, the b squared becomes the more significant term. And remember, for your hyperbola, your eccentricity is greater than 1. So, less 1. So your ellipse is greater, for your hyperbola is less than. Hang on, I've got that back to front, don't I? Probably. greater than 1. That was right originally. Greater than 1. Okay, so greater than 1 for your eccentricity, that's what you're looking at for when you do your calculations. When you've got a hyperbola, you're expecting your value for E to be greater than 1. When you're doing your ellipse, you're expecting your value to be less than 1. Okay, so if there's not that condition, that means all your points are going to be out of whack. Right, so make sure we've got that. Right, same sort of conditions, what happens when you have the centre, everything shift, and that again is all in your notes in there. Right, any questions on the interpretation of that? Right, let's try a couple of questions. Right, so we want to sketch that hyperbola. We need to show the foci, directricity and asymptotes. Okay, so a couple of things you need to think of while we're tackling this question. Is the foci going to lie on a horizontal plane or in a vertical plane? Horizontal. This is really your x squared over a squared, take away y squared over b squared is 1. Right, so that could be your standard form. Okay. We expect your x to be positive, so that means your foci will lie on the horizontal plane. Alright, so we've got centre at -1 and 3 for your h and k. Right, so we need to determine the foci, directricity and asymptotes. So before we can do that, what do I need to do first? Okay, so the formula is what? Okay, so when you've got your hyperbola, the foci lying on the horizontal, the A will become your significant variable. Okay, so there's quite a few things you need to remember. There's quite a lot of things that are very similar, but have their subtle difference. Okay, so a formula sheet for all your different types would be very handy. Right, so you can reference it pretty quickly and hopefully start to remember it. Otherwise, we're going to have to learn, I've shown you already, how to derive them. Okay, so you need to work out what you're going to do. Right, so 4 squared plus 9 squared, 4 plus 9 over 4. So E is going to be root 13 on 2. And you take the square root. Okay, so this sort of question will probably be worth about 3-4 marks at least. Okay, most of the marks are coming from the actual working, and you're going to have very limited 1 mark, no more than 1 mark I imagine for the actual sketch. Okay, so just like when we did the harder sketches in cartographs in extension 1, you had to work through all your asymptotes and all that sort of stuff to work out where the graph is, and your majority of your marks coming in there. Alright, foci. Right, so what's normally the coordinates for the foci? If it was at the centre at the origin. Okay. Yeah, let's go back a step. Let's consider the hyperbola at the centre, or the ellipse at the centre. What is the equation of the foci? Or the coordinates, sorry, the foci. Yep. So normally it's AE, comma 0, right, normally. However, we've got the shift from the centre, okay, so we're really going to be at -1 plus or minus AE. So we're going to go either side of the X value, and then the Y value, well, we're going to have the same value as the line with the centre of your hyperbola. Alright, so the directrices, will they intercept the x or y axis? So if the foci are horizontally across here, okay, and you've got your curve going like that, alright, so would you expect your directrices to be vertically or horizontally? Vertical, so they'll cross the x-axis, okay, so that's your equation starting. Okay, so what's normally the equation directrix if the ellipse or hyperbola is at the origin? So the foci is AE, the directrix is A over E, the equation for directrices plus or minus. Okay, but because of the x value has been shifted, alright, it's going to be -1 plus or minus A over E. Okay, so either side of that centre. So A is 2 and E is root 13 on 2. Oh, sorry, not right. -1 plus or minus A times E. So we root 13 and 3. Let's multiply. Alright, so when we're dividing by a fraction, we're multiplying by the reciprocal. And 81 plus or minus 4 on root 13. Right. Now, in your notes, I have provided for you the equation of the asymptote. Okay, but if we consider the rectangle that we're about to draw, we can use that rectangle to be able to find the equation of the directrices. Okay, instead of remembering another formula. Right. So we've got the centre at 1, 3. We know A is 2 and B is 3. Alright, so we're going to draw the rectangle. Okay, so remember the major axis is length 2A and the minor axis length, so the transverse and the conjugate axis for the hyperbola is going to be length of 2 times 2 and 2 times 3. Okay, so the overall length is going to be 4 by 6 rectangle that we need to draw with the centre at -1, comma 3. Okay, so we consider a rough sketch first, just to get everything in the right spot before we do a good one. Okay, so we know the centre is at -1 and 3. To draw your hyperbola, we can first draw this rectangle. Okay, so really what we're doing is we're going to go up B, down B, to the left A, and also to the right A for that dimension of that rectangle. Okay, so the rectangles, remember A was 2 and B is 3. So really we're drawing a dimension 4 length by 6 height with the centre at -1, 3. Okay, poorly drawn. Right, so that means this dimension is going to be -3, this is going to be 1, and this is going to be 0 because it's 3 down and then 3 up, so I mean this one's going to be 6. Okay, that gives you your rectangle. When you draw that rectangle, we can draw your directrices, your asymptote, sorry, corner to corner through the centre. Alright. So that's how we can get the asymptotes in the right spot. Right, so to determine the equation of the asymptotes, you can either go back to the formula that I've provided for you in that section, or if we use your mathematics skills, okay, we can use 2 points and use your point gradient formula. Okay, so if I know the centre is at -1, 3, and let's take this point here, okay, so from the dimensions of the rectangle is 1, 6. Okay, so what we can do is calculate the gradient. So it's going to be 6 take away 3 over 1 take away -1. So it's going to be 3 over 2. Alright, so I'm finding the gradient of this line here to get the positive slope asymptote. And y take away 6 is going to be 3 over 2. X take away 1, picking the positive point. Probably should put it in gamma form. So 2y take away. Okay, so that's going to be the equation of the asymptote going that way, using the 2-point formula. And for the other one, you can either do the same sort of approach. We know the gradient is going to be -3 on 2. Alright, because we've got the negative gradient, negative equivalent. Okay, and then I've got to pick a point that's appropriate. Okay, so I can either use that centre, that point, or this point. Okay, so we're probably going to use that one because it's not straightforward. And the point 1, 0. Right, so we can get the equation of the downward slope. And there's your equation of your two asymptotes. Okay, so this will work if you substitute into the formula that's in the previous page. Okay, but if you want to remember another formula or you're happy just to work it out using your mathematics skills, that will be up to you. Alright, so I'm going to leave it at that, because we know we've found everything. So from that, we need to be able to sketch it. Okay, so I would suggest you always do a rough sketch first to get the general layout, make sure you're happy with everything that's there. Okay, and then once you've done your rough sketch, then you focus a bit more detail on your more accurate, proper sketch. Right, so that's how you find all the bits and pieces, and then from that, okay, so you can completing the rough sketch. So the hyperbola will touch those 2 points there. Okay, your foci will be here and here, and your vertices will be inside the rectangle, approximately around there. Okay, so you need to write down all the bits and pieces of your information into the corresponding bit. So these sketches need to be quite large. They need to be about 1/3 of a page, I reckon, to get it all looking presentable and keep your markers happy. Alright, any questions from that? So I'm going to move on. Right, so we're going to move on and have a look at this, parametrics. Alright, so we're going to look at the parametric forms of both the ellipse and the hyperbola today. Right, so first we're going to consider the circle of radius A. Okay, so we know that this equation of that circle, x squared plus y squared, is equal to which is A squared. Okay, so we pick a point P on your circle there, okay, so we join up perpendicular straight down, okay, so you pick the point P, alright, join your radius up to that point, drop the perpendicular down, okay, so we have a right angled triangle there, okay, so of course got a distance x and y. And then we can come up with a couple of equations. So the hypotenuse is A for the radius. So I know that x over A, so we've got the adjacent to the hypotenuse in respect to theta, which is your three trig ratios, adjacent and hypotenuse. Okay, so cos theta. So x is equal to A cos theta. So the x value will be whatever the radius is times cos theta, whatever the angle you're up to. Alright, so y over A. Alright, so in the diagram I've got the opposite to the angle theta over the hypotenuse A. Alright, so what's the opposite over hypotenuse? So sine theta. So y is equal to A sine theta. Okay, so that's your parametric for your circle. Okay, so we're representing with a parameter with the angle formed at the centre, theta, and that's how you get your two values, your x and y coordinates, so that you can plot the circle. Right, which really makes sense because what I can do is from this one, number one, the left hand side is x squared plus y squared from the formula. Okay, if I substitute x and y here, A cos theta all squared plus A sine theta all squared. Okay, so I've got A squared cos squared theta plus A squared sine squared theta. Now I've seen cos squared plus sine squared before, that equals 1. Okay, so A squared times 1, which is A squared. Which is right hand side, so that's why it works. Okay, so we come up with a parametric and we put it back and look at it in Cartesian form, okay, and it works. Right, so we've done that to better illustrate what we're doing here. Alright, so we've got our ellipse, okay. Alright, this point P here is, sorry, that point there. Not on the circle I've got there. What I've done is drawn the circle A, radius A, and also the circle radius B. So inside and outside the ellipse, but still touching the respective boundary. Okay, so using that, I can use my do the same sort of thing. So pick a point P up to make the angle of theta in the centre. Okay, and I'm going to use the big and the small triangle, the big and the small circle, to be able to get the information I need. Okay, so actually I was going to use that point. Let's just do that. Right, so I am going to use that point. Right, so just like before, so when we did the x value, right, so we know the distance from here to here has the value for x, right, so whatever that is, and the radius, so the point up here to P, for the circle, is really the radius of that circle, so that's A. Okay, so x over A is cos theta, just like the previous page. So x is A cos theta. So what I'm going to do now is use that smaller triangle, the small triangle within the smaller circle. Okay, so I'm going to use that triangle there. That triangle. Okay, so we've got that little distance x there. Okay, so we've got the little distance y, so whatever the distance horizontally and vertically. And then the hypotenuse is the same as the radius for that little circle. Okay, so from that triangle, y over b, so the opposite over the hypotenuse, okay, is equal to sine theta. So y is b times sine theta. Okay, and there your parametric so for your ellipse. The x is a cos theta and y is b sine theta for your ellipse. Yep. Anything you need to say? Any question? So, write down the Cartesian equation for the ellipse defined by x equals 4 cos theta and y equals 6 sine theta. Okay? Any ideas what this question is wanting you to do? Yeah, so we need the Cartesian. Okay? So, x equals a cos theta and y equals b sine theta. Okay, what is your Cartesian form of an ellipse at the centre? The centre at the origin, sorry. Yep. Okay, that's your standard equation, and that's how you get your a's and b's over there. Okay, so x squared on 16 plus y squared on 36 is 1. Okay, so to go back the other way, if you're given this and then to write that, right, just need your a's and b's and put it into the format of your parametric equation. Okay, so x equals a cos theta and y equals b sine theta are your parametrics for your ellipse. Right, so what are the parametrics for the ellipse of that equation there? So now we don't have the centre at the origin, so we're going to have something a bit different to what we've already got for our parametric form. Okay, so previously we had x is a cos theta and y is b sine theta. Okay, so we're going to use that. However, this is assuming that we're at the centre. Okay, so when we're not at the centre, we're just going to have to do a bit of manipulation. So really, x plus 1, so the point there is equal to a cos theta. Alright, a squared is 4, so a is going to be 2. Alright, so x is going to be negative 1 plus 2 cos theta. So you take what's here, y take away 3, and that is b sine theta. So normally it's y equals b sine theta for your parametric. That's assuming we're at the centre. When you're not at the centre, you're going to have to include the rest of that value up there. Okay, so y is going to be 3, so move it over the other side. So b squared is 2, so b is going to be the square root of 2. Okay, and they're parametric. But if you don't believe me, what you can do is substitute x and y into there. You have all this plus 1 all squared, divide by 4, and then all this take away 3 all squared, divide by 2, and the result will be 1. Okay, if you don't believe me. Alright, now something to grapple your heads around. So given that the coordinates of the foci, okay, are that, and the point P, so that's a movable point here, okay, is A cos theta and B sin theta. So you need to know that that's representing your ellipse, okay, A cos theta and B sin theta. We need to prove that SP is that and S prime P is that. So they're showing you two different foci, and then we need to show that the distance between the two foci is 2 times the value of A. Okay, so by definition, we've got SP, so the point from the foci to the point P, the distance, from the point to the foci P, from the focus to the movable point P, over the distance from that movable point P to the perpendicular point on the directrix, okay, equals what? Eccentricity. Okay, so SP is going to be E lots of PD. Alright, let's consider a sketch. So we've got your foci at here and here, approximately. Right, so as you draw the ellipse, okay, so we've got the point P, that's S, okay, and then out here somewhere is that point D. Okay, so this distance over that distance is equal to your eccentricity. Okay, so this, we need to now write down an expression for the distance of the interval PD. Okay, so in other words, we need that distance there. So what can I write down to have that distance? Isn't it really this whole distance here? Take away that distance here. Give me the remaining bit there. Okay, so the distance, whole distance there. So what is this? The value for the x? What's the x value for that point D there? What is this line? Directrix. What is the x value for your directrix? What's your equation of directrix? Yep. Okay, so absolute value, because we're finding a distance. Okay, so A over E. Take away. Because now we want to take away this section here. So what is the x value for that point P? Okay, because I've given you that coordinate. Okay, so equals the absolute value of A minus AE cos theta. Which is A 1 minus E cos theta. Absolute value. Okay, so a couple of things I need to consider. Right, so I know that for the ellipse, the eccentricity is less than 1. Right, the eccentricity less than 1, I know that cos theta is going to be less than or equal to 1. Okay, thinking about your cos curve. Okay, so the value, y value is going to be less than 1 or equal to 1. Right, so if I multiply two numbers which are less than 1, the result is also going to be less than 1, isn't it? Okay, so E cos theta is going to be less than 1. One takeaway number less than 1 is still going to be positive. The one takeaway E cos of theta is going to be greater than or equal to 0. Okay, so in other words, I'm just showing that it's positive. Okay, so we've done that first bit, so we've shown that. Okay, we also need to consider the values for what's happening inside. Now I need to show that. So S prime P. Right, so we're going to consider the directrix on the other side. Here. Okay, so of course that's your eccentricity, same value again. S prime P is equal to E lots of P D prime. Okay, so equals E. So we need the distance PD prime. So we need that whole distance there. Okay. Now isn't this the x value of this plus the x value of that? Because they're on either side of the axis. Right. So it's going to be A over E plus E cos, so A cos theta. Just write it in the same format as up there. Okay, so it's going to be A, when I tidy it all up, A outside 1 plus E cos theta. When I expand and factorise the A out, 1 plus E cos theta. Okay, so we've already established that it doesn't matter because we're adding, right? So this is going to be a positive distance because we're still adding a number less than 0 to 1. So it's going to be positive, right? So now we've shown that, we now need to show that the distance between those two foci is 2a. So in other words, the distance from here to here is 2a. No, that's not correct. Sorry, scrap that. SP. So if you pick that point P here, okay, so SP, so this distance here, plus S prime P plus this distance here is 2a. Okay, so in other words, if I shift that bit over here, I'm really finding that whole length there. But that works for any point P. So if I put a point here, we've got that plus that is also equal to 2a. Okay, that's what we're getting at. So therefore, SP plus S prime P equal to A 1 take away E cos theta plus A 1 plus E cos. Okay, so I can ignore the absolute value sign because I've already established that they are both going to be positive. Okay, so a bit of expansion and tidying up. However, I know that both got a common factor of A at the front. This has a negative E cos theta, that's a positive E cos theta. So really, these two are going to cancel when I expand, giving me a negative A E cos theta plus A E cos theta. And I'm left with A plus A, which is 2A. Okay, so you pick any point P on your ellipse. Here, any point at all, the distance between the foci to that point will always have the length 2A, no matter where you put that point around your ellipse. Okay, and that is the handy property for you guys to keep in mind. Alright, question. Are we getting there? Somewhat?